Hello everyone, welcome to the channel. Let's understand our planet. In this channel, I'll discuss about how and why our planet works as it is, we can see. In other words, like I'll talk about geology to be specific. To start with that, we have to first see a series on crystallography and basic mineralogy. Like the base of geology, mineralogy and crystallography is the base of geology. So without understanding what is that, without understanding what minerals are composed of and how they work, we cannot move on to the further parts. Then we'll move towards the main subjects. So let's start. So welcome to the series on crystallography. In the first video, this is the first video in the crystallography series, we'll talk about chemical compounds. So because crystallography is nothing but the chemistry of the compounds and the structure of how the bonding is there, we have to talk about chemical compounds first, then only we can move about to crystallography. Going with the basics, elements. So like everyone knows what elements are. Even a school kid would give the right answer like what elements are. So there are about 119 elements in the periodic table, about out of which 92 are naturally occurring. Of course, not all of them are available in good quantities. Many of them are so rare that they are really available in very less quantities, which are not usable to man. So anyways, let's see some of the examples. We have iron, bismuth, hydrogen, and lead, and others, etc. So let's move on to the period. So this is the modern periodic table. Okay, I need not extend much about this. Everyone knows what modern periodic table is, but let's go on with some basics. So the modern periodic table is divided into four blocks. We have S block, we have F block, D block, and the P block. Okay, so we have in the S block includes some metals like non-metals, hydrogen and helium. These are two of the gases. Actually, helium should be placed here, but because of its electron configuration, it is placed under the noble gases, but it's not a noble gas. Okay, and then we have metals like sodium, lithium, magnesium, which are commonly called as alkali metals. Okay, moving on to F block. F block includes two series, the lanthanide series and the actinide series. Lanthanide series includes some of the partly radioactive minerals like lanthanum, cerium, prasminium, neodymium, etc. And then we have actinides, which are highly radioactive elements. For example, thorium, uranium, plutonium, americium, for etc. And then moving on to D block. D block is like totally transition metals. All of the transition metals are present in D block. We know transition metals. The commonest are iron, manganese, cobalt, nickel, copper, silver, gold, platinum, etc. Then in the P block is kind of a mixture. It includes metals. These are the metals actually. Okay. Even these are metals like aluminium, germanium, stibnum, polonium, tin, bismuth. These are metals. This dashed line, this dashed line is actually a line which separates metals and non-metals. Okay, this side is totally non-metals. Okay, but mineral like elements which are nearer to this line, for example, we take silicon, we take arsenic. These are called metalloids. Why metalloids? Because they share properties with metals and non-metals. Okay, they are called metal. They are like actually in between them. Okay, then we have these non-metallic elements: carbon, nitrogen, oxygen, phosphorus, sulfur, selenium. Okay, then these are halogen elements: chlorine, bromine, iodine, acetylene, etc. And on the last column we have noble gases. Noble gases have their electronic shells fully filled, so they do not usually react with anything. So this is the actual structure of the periodic table. Okay, so let's move on. So after knowing the periodic table, we'll move on to molecules. So as we know that elements are usually not stable in the native state because of their electronic configuration, because like except for noble gases, every element is having an valence electron. Okay, valence electrons are those electrons which are either extra or they are less than the electron configuration, which makes them stable. So an atom needs to have the shells filled so that they can become stable. Okay, so to do that, they usually bond with each other. Okay, suppose I take an example of hydrogen. Okay, hydrogen is having one electron in its outer shell. Okay, so according to the law of atoms, uh, it should have two electrons to complete the first shell. Okay, so what the hydrogen will do, it will just come near another hydrogen atom. Okay, this one is also having one electron. Okay, so what they will do, they come together, they form a kind of bonding with each other, like they do the sharing of electrons, we call it. Okay, sharing of electrons. So they share electrons with each other such that the hydrogen, okay, it will have one electron here, it will have another electron here, okay, and this is another hydrogen nucleus. Okay, so okay, it's like this. Okay, or you can write it like this: hydrogen bonding with hydrogen. So it gives us actually a molecule of H2. Okay, so in this way, atoms should bond with each other, like they generally bond with each other or with other elements to form molecules. Okay, so that's what I said. They bond with each other to form molecules which are usually stable. Okay, they have their shells filled, and which essentially makes them electrically neutral and stable. Okay, so let's move on. So let's talk about some of the common molecules that we know. Okay, so water is H2O, is the simplest molecule that everyone knows. Okay, then we have common salt NaCl, and then we have methane, ozone, hydrogen, and helium. So so this is the molecule of water. Okay, this is a molecule of water. So there's one oxygen molecule which is bonded with two hydrogen molecules. Actually, oxygen molecule, I mean the ion of oxygen is having charge of -2. Okay, and hydrogen is having +1 and here +1. So what is happening here? One electron of oxygen is shared with one atom of hydrogen, and another electron of oxygen is shared with another hydrogen atom, such that it forms a molecule of water. Okay, it's like this. Okay, so this is a covalent bonding of water molecule. Okay, similarly we have ozone molecule, but instead of H2O we have O3, three oxygen atoms bonded to each other. Okay, so we will move on to the next one. Coming to our topic, so what is a compound? Chemical compound is any substance that is composed of identical molecules containing atoms from more than one chemical element held together by chemical bonds. So essentially, when these molecules, what we saw, like suppose for example, when we take sodium chloride molecule, okay, so when sodium chloride molecule they come like a group of molecules of sodium chloride, when they come together, they form a compound called as sodium chloride or common salt. Like it's essentially a three-dimensional network that is formed between the molecules. Like I'll give an example. We have this NaCl. Okay, this sodium chloride. Okay, so there's one molecule of sodium chloride. There is another molecule of sodium chloride. Okay, then we have another molecule of sodium chloride. So what these molecules will do, then we have one more. Okay, I'll take one more, NaCl, NaCl. Okay, so we have four molecules of sodium chloride. Okay, so what these molecules will do, they will come together. Okay, according to their charges, they will arrange together according to their charges. Okay, such that they form a three-dimensional cubic network. Okay, okay, they form a three-dimensional cubic network of sodium chloride molecules such that the total electronic charge of this compound stays neutral. It will not have a positive charge. It will not have a negative charge. It will stay neutral, such and that makes it a chemically stable compound. Okay. So, for example, this is a cubic network. Okay, we'll do it we'll explain it in crystallography later. It's a part of crystallography actually. So we have a sodium atom here. Then we'll have a chlorine here. Then we have sodium again here. We have chlorine here. Sodium, chlorine, sodium, chlorine. Then again a sodium in the middle. Okay, in this way, this will bond so that there are an equal number of sodium atoms and equal number of chlorine atoms, and electrical charge remains neutral. Okay, so this networking of molecules makes them stable. So I'll give another example. So atoms of hydrogen and oxygen bond together to form a water molecules. As I said earlier, one oxygen atom will share two electrons with two hydrogen atoms to give one molecule of water. Okay, but one molecule of water will not form a compound. Obviously, it needs lots and lots of molecules of water to form a compound. Okay, so then we have water molecule here. Okay, another molecule here. Okay, another molecule here. Okay, so this molecule they bond together in what we call as hexagonal lattice. Okay, we'll talk about this later, but I'm just gonna say it now. Water molecules bond in hexagonal lattice. Previously, we saw sodium chloride molecules bonded with cubic lattice. Okay, so they formed as a cubic structure. Okay, so sodium chloride, they were cubic lattice. Okay, but water molecules, they form an hexagonal lattice. That is why the ice flakes that we see, the snowflakes, okay, the snowflakes that actually have an hexagonal symmetry, like 6-fold symmetry, when we join these snowflakes, okay, the snowflakes, they have six points, okay, which has an hexagonal symmetry. That is the reason behind this, because we have hexagonal lattice of water molecules. Okay. And let's not go further into this. Okay, we'll talk about this later. This section. So two hydrogen atoms bond with one more oxygen atom to give an water molecule, which comes together. Lots and lots of water molecules will come together to give a compound of water. So compounds are made by bonding of molecules, atoms, or ions. So since bonding is present, we generally classify compounds as either crystalline compounds, okay, or amorphous compounds. It is classified on basis of the nature of bonding that is taking place within atoms. Okay, so we have crystalline compounds. So in crystalline compounds, there's something called as crystal structure. We'll see this on a later video. Okay, here for example, we have copper sulfate. So this is copper sulfate. Okay, it has a molecular formula of CuS, so it's a crystalline copper salt. Okay. On the other hand, amorphous compounds do not have a perfect crystalline structure. Okay, they have irregular bonding. For example, we have glass here. Okay, so glass is actually SiO2. Okay, so let's see how they are actually different in on what basis they are different. Okay, let's see that. So this is copper sulfate, CuSO4. So this is the atomic structure of CuSO4. Okay. And on the other hand, we have glass, SiO2. So we have atomic structure of SiO2. So this is where we get the difference. Okay, this is the difference that we have to understand between crystalline compounds and amorphous compounds. Okay. So for amorphous compounds, we'll see with glass. Okay, so since glass is an amorphous compound, okay, in amorphous compounds we do not have regular bonding between atoms. So as you can see in this structure, okay, the bonds between silica, so this is silica, okay, and this is an oxygen atom, and this is another oxygen atom. So the bonding, okay, this is another oxygen atom, okay. So the bonding which is taking place between these atoms is not regular. You can see one pattern here, but there's another pattern over here, okay, and there's another pattern over here, okay. It goes very differently, okay. It's not having a regular pattern. So suppose if we were to have a crystalline structure in this, it would have a hexagonal pair structure or some other regular repeating structure, but we don't have that kind of structure, okay. So we don't have irregularly bond, I mean we have irregularly bonded silica and oxygen atoms here, okay. We don't have a repeating pattern, so hence there is no specific pattern between atoms in three-dimensional space. Since this is a two-dimensional diagram, we have to imagine it in three dimensions. Okay, so it will not have a specific pattern that is repeating. Okay, in all the three dimensions, all the x, y, and z axis. We know the x, y, and z axis. Okay, so we have to imagine this structure. Okay, in all three directions. This is very crucial in understanding crystallography. Okay, for amorphous minerals, it is like for amorphous compounds, it's not much necessary. Okay, but for crystal compounds like this, to understand the three axes of crystal, okay, it's very crucial in that. Okay, we'll see on this later on the x, y, and z axis. Okay. Anyways, let's move on. So moving on to copper sulfate structure. As you can see in this copper sulfate structure, we have a repeating pattern. Okay, some pattern is repeating. So I'll make this use the red one only. Okay, so you can see this rhomb structure in middle. Okay, okay. So actually, this copper sulfate belongs to rhombic lattice structure. Okay, rhombic rhombic lattice. Okay, I mean it's orthorhombic. Sorry, it's orthorhombic. Ortho orthorhombic lattice. Okay, it actually in 2 dimensions it will be like this, but if we go for 3 dimensions, okay, it would be like this. Okay, the angles would be 90 degrees between the edges, but one of the angle would be greater than 90 degrees. So this is orthorhombic lattice. So copper sulfate is having a regular arrangement of atoms or molecules, and we can see that in this structure. So regularly bonded copper, sulfur, and oxygen atoms. Okay. So thus we have a specific pattern between atoms in three-dimensional space. This is what we generally call as lattice. Okay, Lattice. I mean, sorry, Lattice. So lattice is nothing but the arrangement of atoms in 3 dimensions. Okay, so there are 14 lattices. We'll talk about this on later on another video. Okay, so copper sulfate is a crystalline compound because it has this specific pattern. Okay. So this is how we can know the difference between crystalline and amorphous compounds. So let's talk about the sources of compounds. Since we have already discussed about what are the compounds and how they are differentiated into two crystalline and amorphous, and now it's time for like to know the sources of compounds. So usually we know that chemical compounds can be naturally occurring or they can be synthesized in a lab. So there are two categories, I mean two main sources of chemical compounds. They can be naturally occurring, okay, or they can be synthesized in a lab. So let's differentiate between them. So we have naturally occurring compounds on one side and we have synthetic compounds on the other side. So let's talk about naturally occurring compounds first. So it includes naturally occurring minerals. So why minerals? Because minerals are the only naturally occurring inorganic compounds. Okay, they are only inorganic. Okay, they cannot include organic compounds. Why is it so? That we are going to talk about in another video. Okay, so minerals can only be organic, naturally occurring compounds. Okay, and they can only be solids. Yes, of course, minerals can only be solids. We don't have liquid minerals, we don't have gaseous minerals. Okay, they can only be solids. Okay, why inorganic solids? To be specific, is a topic of a later video. Okay, I'll explain this later because it includes some of the mineralogical knowledge on this. Okay, then how they are formed. So minerals are formed as a result of chemical reactions taking place on or within the earth. So there are a lot of geochemical reactions that take place on the earth. Okay, either on the surface or within the surface. Okay, so the result of these geochemical reactions, okay, we get many different minerals. There are about 5,000 minerals. Okay, 5,000 known minerals. Okay, so you can understand the extent of how different chemical reactions are taking place within the earth. Okay, so minerals make up most of the planet Earth. Okay, so since they are the essential part of rocks, and rocks are essential part of the planet Earth, so we can say that they make up most of the planet Earth. And yes, we have one more point to add here. Okay, I forgot to add. So we have organic compounds, naturally occurring organic compounds. Okay, where can we find this? Okay, they are found in humans, animals, humans, animals, animals, plants, And another living beings like you take fungi. Okay, so fungi, they have organic sugars. Okay, it's actually end here. Okay. Fungi, they have organic sugars in them. Plants have lots and lots of organic compounds in them. We humans have organic compounds within us. Animals also have. We have fatty acids. We have DNA, RNA. These are all organic compounds. And we also have some inorganic salts. Okay. Even in plants, we have some inorganic salts. Okay. So this is the like one of the another important source of chemical compounds. Okay, on Earth. So in living beings, we can find some organic compounds. Lot of organic compounds are found in living beings and some inorganic compounds. Okay. Moving over to synthetic compounds. So synthetic compounds do not include minerals, and yes, obviously they don't include this. Okay, but they include compounds that are usually synthesized in labs. Okay, so suppose we want to make calcium carbonate. Okay, we want CaCO3. So what we will do? If we want to take a naturally occurring CaCO3, we'll go on to a mineral called as calcite. Okay. So this is a natural source of CaCO3, a mineral called as calcite. Okay. But if we want to make it in a synthetic mineral in laboratory, what can we do? We all know this reaction. Okay. So it's CaO calcium oxide plus CO2. So when we pass CO2 gas in hydrated lime, it becomes CaCO3 as a precipitate. Okay. So this is how we can synthesize calcium carbonate in a laboratory by using hydrated lime and CO2 gas. Okay. So this is how we can make synthetic compounds. So it's generally done in laboratories. Whatever chemicals that we get in markets or you can say shops, those are all synthetic. Okay. And yeah, when we talk about minerals, minerals are usually used in industries. Okay. They usually use as ores of metals. Okay. And they also have other industrial uses. We need not talk about this here. Okay. So yes, and synthetic compounds can also be solid, liquid, or gas. They don't have restrictions. They can be anything. You can create any synthetic compound in a laboratory, whether it be a solid, whether it be a gas, or whether it be a liquid. Okay. We don't have restrictions on this. So let's talk about some examples. So here, so for naturally occurring compound, we have quartz. So this is a cluster of quartz crystals. Okay. So quartz is having molecular formula SiO2. It is very similar to glass, but there is a major difference between quartz and glass. What it is? Glass is an amorphous compound. Okay, glass is amorphous. Okay, but when we talk about quartz, quartz is actually crystalline. You can see crystals in this picture. Okay, crystalline. They only share same molecular formula, but their molecular arrangement is very different. So this is a crystal of quartz. You can see a perfect shape. Okay, actually, the molecular arrangement of atoms decides the physical shape of the crystals. Okay, so for quartz we have hexagonal lattice. Okay, hexagonal lattice. Okay, quartz is having hexagonal. lattice. That is the reason why quartz is having six faces, six sides of a crystal. Okay, it is having like when you see from top, it will have an hexagonal shape like this. Okay, when you view it from top, I mean, sorry, when we view it from top, it will have an hexagonal shape like this. Okay, so this is crystal of quartz when viewed from top. Okay, and when we view it from here, from sides, okay, it will have a structure like this. Okay, so this is a quartz crystal. It will have a structure like this. Okay, so it is having an hexagonal lattice. So the internal makeup of the atom describes the external form of the crystal. Okay, so we'll not go into much detail. Okay, so just leave it here. We'll just continue in some other video. Okay, and for synthetic compounds, we already know what this is. So this is copper sulfate, CuSO4. So this was prepared by many chemical processes. The commonest one is like reacting copper with either copper oxide or copper hydroxide with sulfuric acid, so we can get copper sulfate salt. Okay. As an acid and bases react to give a salt and water combination. Okay. So this is a common process that we use to prepare CuSO4. Okay. So moving on. So one thing that we should note, most of the inorganic compounds occur both as minerals and can also be synthesized in a laboratory. Okay. For example, I'll take, uh, okay, let's talk about calcium carbonate. Okay, calcium carbonate. We can synthesize this in laboratories. Everyone was certain that. It also occurs as a mineral, okay, as calcite. Okay, calcite mineral. Okay, so like no, but not all of the compounds which occur as mineral are synthesis in laboratories, or not all of these compounds that are synthesized in laboratories are found as minerals. It's not totally inclusive theory. It's partly inclusive, okay. And yeah, one of the most important thing, okay, their properties differ from the natural mineral form. Okay, when we talked about calcite, okay, okay, this is calcite, okay, calcite, and then we have CaCO3 synthetic. I mean, no, we cannot say synthetic, it's lab generated. Okay, let's make it like this, calcite and CaCO3. So this is crystalline compound actually. Calcite is a crystalline compound or a crystalline mineral. But when we talk about CaCO3, it's actually an amorphous powder. When we are creating in a lab, okay, amorphous white powder. Okay. CaCO3 is amorphous in nature, but calcite, which is all having the same molecular formula, the same chemical makeup, is actually crystalline. So we can see that the properties of minerals are very different from the properties of their lab synthesized chemical counterparts. Okay, let's see another example. Okay, we have iron 2 sulfide. Okay, so this is iron 2 sulfide. It's a dull looking gray colored compound with molecular formula FeS. Okay, so it's a lab synthesized powder. You can just add some hydrogen gas, okay, hydrogen sulfide gas to Fe chloride. FeCl3 plus H2S gives FeS. I know this is not a balanced reaction, but this is what it happens, okay, in general, in laboratories. So it's an amorphous, dull-looking black-colored powder. Okay. On the other hand, we have a mineral counterpart of this compound, which is called pyrite. So this is pyrite. See the difference? This is an amorphous, dull-looking powder. This is shiny, metallic mineral, and it's also crystalline. Okay. So a lot of difference is there between these two guys, but only similarity is their molecular makeup. They belong to a same chemical compound. Only the origin is different, which makes their properties different. Similarly, we have red copper oxide, CuO, which is red amorphous powder, and then we have its mineral counterpart, red colored crystalline cuprite mineral. And then we have another example of basic copper carbonate, CuCO3, OH twice, bluish green aquamarine color, okay, aqua colored dull powder, and its mineral counterpart malachite, same chemical formula but different physical properties. Okay, so here it ends. So we'll continue in another video of this series. Let's see in the next video. So in the next video, we'll talk about some basic mineralogy and some of the properties of minerals. Okay, then we'll move on to crystallography. Okay? So to be continued. Okay. Thank you for watching this video. I hope that I have explained in the best possible way. Hoping that you have liked this video. Thank you, and let's see you later. Bye. And please do like, subscribe, share. Bye, guys.